Okay, hi everybody. So problem 12. When is a sequence bounded? Okay, so that you just have to know that definition. It's in the book, and you should really just know it immediately. And I guess what I mean is be able to construct it within 30 seconds by thinking about what does bounded mean, picturing something, and then reconstructing the precise definition of when a sequence is bounded. That should take roughly 30 seconds for you. So pause and try that. If not, go to the book. Which of the following are bounded and which are unbounded? So this one is unbounded, bounded, 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 unbounded, bounded. And then this one I deleted because the question of whether it's bounded or unbounded is extremely complicated. Depends on whether this number C was chosen in the Mandelbrot set or not, or where it was in the Mandelbrot set. And so that I deleted that problem. What is the Archimedean property of R? So this one, go to Wikipedia and look it up. Read it, try to understand something about it, enough to remember what it is when you're prompted with this question. Okay, problem 14. Draw a cartoon illustrating a convergent sequence in C. Label and explain your cartoon using words and formulas. So basically, this is asking you to remember and explain the definition of a convergent sequence. There is a picture in your book with this. Now, very similar is problem 15. So these are poorly written on my part. These are basically the same problem, except maybe this one wants you to label the cartoon and explain the cartoon, and this one wants you to note the various notations and terminology that are used. So let me just at least talk about these two questions for a bit. Okay, so when is a sequence convergent? Illustrate a convergent sequence. Basically, here we go. Okay, so a sequence converges if basically there's some number W such that around W, if you choose any little tiny ball, no matter how small the ball, only finitely many Z sub n are outside that ball. On the surface, this looks different than what's in our book, but it is equivalent, and it's another way, I wanted to say it's another way to think about it. So this is Z1, this is Z2, Z3, etc. And, for any small ball of radius, well, the radius should be a positive number. For any small ball of radius, only finitely many Z sub n are outside that ball. And that means that, really I should have put, there is some W in the complex numbers such that for any small ball of radius d around W, or centered at W, we have only finitely many Z sub n are outside that ball. Now what that means, to prove this, that means we need to find exactly how many of them are outside the ball. So for any D, we need find a cutoff point. Whatever is the last one that's outside the ball. There should only be finitely many. So basically the entire sequence, infinitely many points of the sequence are inside any ball of any size we want. So for any size ball, we need to find some cutoff, maybe n sub d. It depends on d. Depends on how small of a ball we choose. Such that, this is an abbreviation for such that, because mathematicians are too lazy to write such that. We need to find n in n such that past that point. And I don't know, you could write this too. Either way works. It's just going to change your n for a specific d. Implies that we're inside the ball. Now note, what's really important here is that I can fluidly go back and forth between my picture of being inside a ball and this formula. This formula means inside the ball, inside a ball, centered at W, blah, 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 blah. It has that meaning, and you need to be able to fluidly go back and forth and just know that this formula means that z sub n is inside a ball of radius d of W, okay? Z sub n and W have distance less than d. They are within d of each other. Okay, and this means infinitely many parts. Like all these parts of the sequence are in there. That means that, and that's the cutoff, which means only finitely many z sub n are at the ball. That means z1, z2, z3, all the way up to zn minus 1 are outside the ball. That's only finitely many. Z1, Z2, Z3, all the way up to Z capital N minus 1 are outside the ball, because all the other ones are inside the ball. Okay, so that's a good picture. I drew a cartoon and I labeled it with words and formulas explaining what's happening. Now let's look at some notations and terminology. So if we're notating our sequence like this, z sub n, as often is done, when we don't have an explicit formula, maybe if we had an explicit formula like that, then we could talk about that, but often it's nice to hide it in this symbol. And we would say z sub n goes to W. Okay, and this is a symbol, symbolic shorthand for what? For the sequence n maps to z sub n converges to W, where W is a complex number. And these are words, and this is a symbol for it. Another symbol for it would be lim n goes to infinity z sub n equals W. I really don't like this because this doesn't really tell me that n is a natural number. It sort of suggests that n could be a real number, and then we'd usually write x for the variable name. But anyway, so just the choice of variable name is supposed to tell me that I have a sequence of natural numbers, and I don't like that. I like I guess neither does this, but for n and n, I don't know. The purpose of a symbolic shorthand, no matter what it is to hide details. And when you hide details, then they're hidden. They are hidden. And so you run the risk of confusion. And so sort of that's just what we deal with in math, because you can't be writing out all these words every time. And it's really useful to hide details. And so it only becomes useful when these symbols are fast. You can look at one of these symbols and decode it into precise words / formulas. So when I see this symbol, what I think is this right here, okay, or I think this. And to go from there and unpack the details, is crucial. It's just, you have to practice it so that it becomes more and more natural, okay? And and then you'll be able to do things with this, like prove things. But to make proofs easier, you first have to just make the symbols more natural, okay? It's like if I asked you to prove something in a language you didn't speak or read, it would be much too difficult. You have to learn the language, you have to learn the symbols, and make them fast and easy, so that the actual proofs, which will involve more concepts and more tricks, maybe not tricks, but like you want your brain to think of these very easily and fast. And so that takes practice, because if your brain makes these easy, then later when you prove things, you've freed your brain to think about the new concepts. And how different concepts relate to each other. Okay, so that's problems 14 and 15, which were vaguely written by me.